Okay, so we can start our session here on apps and security. And welcome to everyone, and welcome also to our speakers, of course. The first speaker is Ting Ting Yin, and she's presenting an empirical study on implicit constraints in smart contract static analysis. And she will be presenting for 5 minutes, and we will have 5 minutes presentations, and at the end we will have a plenary discussion for after the presentation for half an hour. So if you have questions, please write them down in the chat, and I will allow you to ask the question, and I will moderate. Okay. So thank you, Tintin. Please start.
Okay, thanks for the introduction. And I'm Tintin from Tsinghua University. And today I'll talk about a work of the smart contract and static analysis. Contracts in blockchain are usually financial related, which makes them attractive attack targets. So many static analysis tools have been developed to facilitate the contract audit process. We started this work because we found these tools are suffering from high false positive rate. We tested the tools on real contracts and found 3 types of implicit constraints are common causes of false positives. The first kind of implicit constraint comes from the external variables, which have real-world meanings like time and a site. For example, the sum of message.value is less than the total issued ETH in the Ethereum and cannot cause integer overflow here. The second kind of constraints are from the internal variables. The contract code can only assign specific values to the contract variables. For example, the fund variable in the example is always equal to 10,000, so the multiplication in line 7 will never be overflow. And lastly, there are implicit constraints between internal variables. A group of storage variables in contract may always get updated together to keep certain invariants. For example, the balance of the contract is always equal to the sum of receiving money. These 3 types of constraints can significantly affect the performance of static tools, such as causing errors in reachability analysis and resulting in false positives. But are the state-of-the-art tools aware of the implicit constraint? We choose famous open source static tools as research target and construct a comparison experiment via bug injection to answer this question. The result is shown in the table. The red rectangle means the tool meets more than 80% of the constraints, and the green rectangle means the tool meets less than 20 of constraints. We can see most of the rectangle are red, which means the static tools are generally weak in dealing with the constraints. To mitigate this problem, we propose a lightweight mitigation named Consim. The key idea of Consim is to add constraints in symbolic execution procedures. For the constraints on external variables, Consim adds the constraints to the return value of real-world related instructions. For example, we can limit the time-related variables to be larger than the time of the genesis block. For the contract on internal variable constraint on internal variables, Consim concretizes the implicit constraints via concolic execution. Take a common constraint in ERC20 contract as an example. The total supply is the sum of balances array, which also means if the item of balances array is larger than the variable v, total supply will also be larger than v. The variable v here is an user input which can be controlled by the attacker. Traditional symbolic execution can easily neglect the relationship between the balances and the total supply if we initialize all variables as symbolic values without constraints. But if we execute the contract with concrete values before symbolic execution, setting address A and B with 10 tokens, now each address in balances will have 10 tokens and the total supply is 20. The relationship between the value of balances and total supply has been built now. If the contract
1 minute.
Okay. If the contract checks the user input weight is lesser than 10, it will also be less than 20, obviously. So no false positive alarm will be raised here. In this way, Consim imports the implicit constraints into the contract. We compare the Consim and those series on the real-world contracts. Consim can filter out 96% of the false positives and reduce the false negatives by 2/3. The benchmark we used in the empirical evaluation is open sourced, and here are some takeaways. In this work, we found 3 kinds of implicit constraints are resulting in false positives. Most of the static tools cannot deal with them properly, but luckily these constraints can be easily added into the symbolic execution-based tools. The implementation of adding constraints varies from tools to tools, but generally can be quite simple. And that's all I want to share about this work. Thanks for everyone.
Thanks to everyone, and thank you, Tintin, for being on time. So the next presenter is Ruan. Please join the session. I will go out of the session and be back because I feel I have audio problems.
Can you see my screen?
Yes, thank you. Please start. Thank you.
Okay. Hello everyone, I'm Renhan Feng from Shanghai Jiao Tong University. Today I will introduce our work, Automated Detection of Password Leakage from Public GitHub Repositories. In recent years, the GitHub community has been proliferating. The vast majority of developers use GitHub's free code hosting services for version control and collaborative development. With more and more repositories hosted publicly on GitHub, security and privacy issues come naturally. Credential leakage is one of the most serious problems. Specifically, developers may mistakenly upload their code with sensitive authentication information to public repositories. Related news emerges endlessly. For mitigation, both academia and the industry have proposed solutions for credential detection. However, existing tools focus mainly on API keys and cryptographic keys, which usually follow specific structures and can be detected effectively with elaborate regex. In contrast, passwords, which are widely used for authentication, are hard to detect with high accuracy. It comes mainly from 2 challenges. The first is the heterogeneity of passwords, which means passwords could be virtually any strings and do not conform to the distinct structure. The second is the multiformity of source code. Since GitHub repositories consist of code written in different programming languages, following diverse syntax and styles. Therefore, existing tools that support password detection are limited by accuracy or generalization ability. In this work, we propose Pathfinder, an automated approach to detecting passwords in code files written in different programming languages. This is the workflow of Pathfinder. Given a file, Pathfinder extracts hard-coded strings as candidate passwords. We decompose the password detection problem from 2 aspects. Firstly, we focus on the intrinsic characteristics of passwords. Specifically, passwords are not uniformly distributed due to the natural preference for choosing easily memorable passwords. Given a set of strings hard-coded in code files, a human observer can tell which strings are more likely to be passwords, because the corpus of passwords has a different distribution against ordinary strings used in source code. Intuitively, Pathfinder imitates this ability of human beings. We use a deep learning model, that is the password model, to extract the intrinsic characteristics of textual passwords and give a prediction whether the candidate is a password or not. Besides the intrinsic characteristics, we found that the code snips surrounding passwords usually share similar semantics and structures. Therefore, we constructed another deep learning model, that is the context model, to inspect the context of the candidate passwords and give a prediction that whether the code snip is used for authentication or not. as an important basis for password detection. Finally, we ensemble the two models. Only when the password and the context model agree will Pathfinder take the candidate as a password. As for the evaluation, we focus on these three research questions. Both the password and the context model perform well on the respective dataset to measure how effective password is at detecting passwords in source code. We built an end-to-end ground truth. The result shows that Pathfinder performs much better than the baseline. Under the cross-language setting, the performance only slightly declines, which proves the generalization ability of Pathfinder. Armed with Pathfinder, we conducted a large-scale analysis on GitHub. Pathfinder totally discovered over 140,000 passwords from newly uploaded files in 75 days. To further inspect the leaked passwords, we carried out a manual review of the leakage dataset. More details can be found in our paper. To sum up, we propose Pathfinder, an automated approach to detecting passwords in code files written in different programming languages. Pathfinder models both the intrinsic characteristics and the context semantics of passwords to achieve high detection precision. We conducted a large-scale analysis on password leakage on GitHub, which shows that password leakage is pervasive. That's all. Thanks for your attention.
Thank you very much, and thank you for being on time. So the next one is Van Hoang Lee. Van Hoang Lee, please share your screen.
I will share my screen. Can you see my screen?
Yes.
Yeah.
Yes. Hi everyone. I'm Van Hoang from the University of Newcastle, Australia. Today I will present our recent work about log-based anomaly detection with deep learning. Software systems such as search engine and social network or online software has become indispensable part in our daily life. Ensuring high availability and reliability are essential for this system. With the increasing complexity and scalability become inevitable. Anomalies is unexpected behavior that happen during the system runtime and can affect to the performance or security of the system. Only a small problem could lead to data corruption, performance degradation, or even a significant loss of customer and revenues. Therefore, to record critical events, the system usually generate logs. System logs are actually available practically on every software system. This is a very valuable resource to understand system behavior, and engineer can analyze log data to detect anomaly or identify the root cause. Recently, there has been many methods that apply deep neural network such as RNN, CNN, or Transformer to detect system anomalies. They share the common framework that consists of 4 steps: log passing to extract the log event, log grouping to generate log sequence, log representation to extract the numerical feature, and a deep learning model that detect anomalies based on the numerical vector. However, we noticed that several aspects are overlooked by these methods during evaluation. Therefore, to explore the real performance of these deep learning models, we conduct an in-depth analysis. To this end, we evaluate the impact of data training selection strategy and the impact of different degree of noise on the performance of models. Next, we evaluate the impact of data grouping and data pre-processing techniques. And lastly, we evaluate the performance of model with different data quality and the performance of model on real-world scenarios. We choose 5 representative models for our study. Based on our experimental results, we find that random selection could lead to unreasonably high accuracy because of the data leakage problem. Therefore, detection model should separate the training and testing data by time to avoid leaking any training data to testing phase. And the next one, we find that different grouping techniques could lead to different results, and models usually perform better when using grouping by session windows. Next, we find highly imbalanced data can have a big impact on the performance of models. Therefore, more evaluation metrics should be used for a comprehensive evaluation. We also find that the noise from labeling phase have a big impact on supervised model, and the models that use semantic vector can better handle the noise from log passing phase. Based on our finding, we suggest some possible research work. The first one is that the model should be evaluated on a variety of data sets. And the second one is that the model should be able to work with limited label data. And the third one is that the model should be able to detect anomaly as soon as possible so that more mitigation action could be taken. And the model should be able to understand the semantic meaning of logs to handle the unstable log data. And also, we also suggest that more relation among log events should be explored to capture a variety of anomalous behavior. And in summary, we find that we conclude that log-based anonymization is important for software system, and we have investigated several aspects for model evaluation. And based on our finding, we suggest some possible future work. For more detail, please find in our papers. Thank you for listening.
Thank you very much also for being in 5 minutes really sharp. So next presenter is Li Zhen. Please share your screen.
Okay. Hello, everyone. My name is Zhen Li. I'm an associate professor at Huazhong.
Could you go in presentation mode? Presentation mode.
More? Is it okay now?
No. Please. So please go back to the previous. Sorry. Yeah, because we saw the slide and also the outline. Yeah, please go back to the previous setting. No worries.
Okay.
Okay, go ahead, please.
Okay. Hello, everyone. My name is Zhen Li. I'm an associate professor at Huazhong University of Science and Technology, China. This work was done when I was a postdoc at the University of Texas at San Antonio. The work was cooperated with Professor Qian Chen, Ms. Zhou, and Professor Xu. First of all, what is source code authorship attribution? Here is a source code example. The question is, who is the author? Who is the author? Does Bob written that? The authorship attribution methods can answer this. But what if Bob has not written that? So the problem here may be an adversarial example. There are two types of attacks against a single authorship attribution: exploiting adversarial examples and coding style imitation or hiding attacks. The state of the art is the current code authorship attribution methods are vulnerable to these attacks. If the goal of the attacker is to misattribute P prime to a target author Eric, it's a targeted attack or coding style imitation attack. If the goal of the attacker is to misattribute P prime to anyone but Bob is an untargeted attack or coding style hiding attack. Existing attack methods are manual, semi-automatic, or automatic,
Sorry,
not
sorry,
applicable to deep
Zen,
learning-based
sorry.
method. Yeah.
Sorry.
What?
We don't see, we just see the first slide. I think you are in other slide, like we see, yeah. We just, we were stuck at the first slide. So if you can
What's the problem now?
Maybe you should
try
first
sharing this, because we see PowerPoint, but not in the presentation mode, in the normal mode. So if you move the slide in the normal mode, it's fine. Like if you go slide 1, slide 2, slide 3.
Okay. I just use this.
Yes. This is what we see, yeah. So if you can go to the slide that you were discussing, okay. Yeah, do this way. Yeah, thank you.
Oh, okay. Sorry.
No worries.
I go on. So our purpose we focus on enhancing the robustness of deep learning-based code authorship attribution against attacks. We propose 2 new attacks, which exploit automatic coding style imitation and hiding. We propose an innovative framework, RobGen. The key idea is incorporate data augmentation and gradient augmentation to learn robust style patterns. We focus on C, C++, and Java programs, and we propose and we synthesize 23 attributes according to the following 3 requirements. We propose 2 attacks. The first attack is automatic coding style imitation attack. There are 4 steps. We extract coding style attributes values, synthesize coding style attribute values, extract from the targeted authors' programs, identify coding style attributes for code transformation, and finally conduct coding style transformations to imitate target author. The second attack is automatic coding style hiding attack. We use imitation attacks by choosing a target author with the highest misattribution probability. There are 5 steps. Steps 1, 2, 3, and 5 are similar to the steps of coding style imitation attack. And step 4 is to select author for transformation with the highest misattribution probability. We propose a RobGen framework to improve the robustness of deep learning data augmentation and gradient augmentation. For data augmentation, we extend the training coding style imitation and manipulate programs by coding style perturbation. For gradient augmentation, we train a robust deep learning model. It involves 5 sub-steps. We train a full-fledged network and several sub-networks. When the model converges, we can obtain a robust model. Our experiments focus on 3 research questions. The first research question is about robustness of existing methods. Existing deep learning based methods are far from robust against known and new attacks. For the second research question is about the robustness of RobGen. And the results show that RobGen-enabled methods are substantially more robust than the original deep learning-based methods. For the third question is about comparing adversarial training. We observe RobGen substantially outperform the other adversarial training methods for attacks. Here are takeaways. We propose 23 semantics preserving coding style attributions and transformations. We propose 2 automatic coding style imitation and hiding attacks. And we propose a RobGen framework for enhancing the robustness of deep learning-based models. That's all, my president. Thank you.
Thank you very much. Thank you. And now we have Yawen Wang. Where is your app frustrating users? You can share your screen.
Okay. Is it work?
Yes.
Okay. Hi everyone. My name is Yawen Wang. I am a PhD student from Institute of Software, Chinese Academy of Sciences. Thank you for listening my presentation about our recent study. The title is "Where is your app frustrating users?" This study is about information extraction from app reviews to facilitate developers to improve the quality of apps. Users often write reviews of apps to provide valuable information to developers, such as user experience, bug reports, and so on. So, firstly, let's look at what users are complaining about in app reviews. The first level is what aspect. That is the high-level topics or aspects of the reviews. And the second level is where aspects. Users are complaining about some specific app features and they think these features might have problems. And the final level is other aspects, mostly are some trivial information. And in this study, we focus on where aspect, that is which specific app features the users are complaining about. So in this study, we define phrases buried in app reviews which can reflect users' complaints about certain app features as problematic feature. And for example, the problematic features from the left three reviews are these phrases. And the problematic features have many potential application scenarios, such as bug location, bug recommendation, GUI testing, and competitive analysis. So the question is how to automatically extract problematic features from app reviews. And we propose an approach named Sira to extract, cluster, and visualize the problematic features of apps. And it has four steps. First, it pre-processes the app reviews crowd from online app markets to obtain the cleaned reviews descriptions and the real attributes. And second, it builds and trains a phrase extraction model to automatically extract the feature phrases. And the model combines the review descriptions and two review attributes as input to better model the semantics of reviews. And third, Sira clusters the extracted phrases with a graph-based clustering algorithm to summarize the common aspects of feature based on their semantic relations. And finally, it presents a visualization view to illustrate the summaries and compare the features among different apps. And this is the dataset. We use the reviews of 6 apps from 3 categories as our experimental data. And we answer the following 3 research questions. RQ1 is to investigate the performance of feature extraction. RQ2 is conduct comparison with Sira's 3 variants to demonstrate the contribution of each review attribute in phrase extraction model. And RQ3 investigates the performance of Sira in problematic feature clustering. And for RQ1, Sira outperforms 4 baselines on all metrics in feature extraction. And we also present some examples on extracted features by different approaches. And for RQ2, we construct 3 variants of Sira, and the performance achieved by adding both of the attributes is the highest, further indicating the advantage of our model design. And RQ3, we use LDA and k-means as baselines to evaluate the performance of clustering, and Sira is achieve the best performance. And finally, we apply Sira on a large-scale dataset to obtain the visualization. And this figure shows the distribution of problematic features of different categories. And the table presents the representative problematic feature of each cluster in the previous figure. And this is a conclusion. And that is all my presentation. Thank you.
Thank you very much. So we have our last presentation from Zhangji, and you can start sharing the screen. We are only 5 minutes late, so it's fine.
Hello everyone.
Please go.
I will introduce our paper towards automatically repairing compatibility issues in published Android apps. I'm from Monash University, Australia. And first, I will introduce the background. The serious fragmentation problem of Android has caused severe compatibility issues for the Android ecosystem. That is, many different Android versions running on different devices released by hundreds of manufacturers. Android phone users often find that some apps can't be installed on their devices or can be installed but will crash later on if a specific function is reached, leading to poor user experience. Actually, there are over 1 billion Android devices no longer supported by Google, and there are more than 24,000 distinct device models running on more than 10 API levels in the market. Each API level supports thousands of APIs. Therefore, the users of those devices will likely encounter compatibility issues, especially when they want to leverage the latest Android apps. Our research community has spent lots of effort on disclosing such issues, including at least these 3 types. And the type is one of the most common types of compatibility issues. The issues are caused by the evolution of the Android framework. During framework evolution, new APIs are regularly added to the framework, and existing APIs are also regularly deprecated and removed. The example given it is the API get type deprecated and SDK level 28 on devices running SDK versions larger than 28. It is recommended to use API has transport instead. And the second type are associated with specific devices running customized Android systems. The problematic apps will only crash on certain devices, but behaving normally on others. This all the devices running the same Android framework version. In this example, the API set recording hint depends on a conditional statement that checks the device identifier against Nexus 4. Only the condition to be true, the corresponding app is indeed running on Nexus 4, the API will be executed. And the third type is caused by the changes to Android system callbacks. Such system callback methods are predefined by the Android system and will be directly executed when certain conditions are satisfied. And lines with a plus sign represent a possible fix for this incompatibility. And the unattached context callback method is only introduced from API level 23. This code is running on smartphones with earlier API levels. This callback method will not be executed, and the M activity field will not be initialized, and its usage will likely throw null pointer exceptions. And as for the repairing work, existing approaches of the first type all come with some limitations, and the other 2 types, there are no tools proposed in the literature until now. So we propose a prototype tool, RepairDroid, leverages predefined patch templates to instrument Android apps in order to fix these 3 types of compatibility issues on released apps. And thanks for listening.
Thank you very much, Zhangji. So we start with this half an hour, actually 25 minutes discussion session, and I see that there is already one question from Kushal. Kushal, do you want to ask the question yourself? So it is nicer. You directly interact with Li Van Huang. Kushal? Yeah, okay. Kushal is facing some issues. So I will ask you the question myself. He says, many applications restrict logging or obfuscate their logs for security reasons. What are your recommendations for such apps?
Yes, thank you for an interesting question. So actually, for now, we didn't consider any obfuscation for logs, and if yes, so I guess that may be some specific information such as username or ID or password will be released from logs. And if there's still some text description of log message, the current work still can be applied. And for some application that restrict logging, I suggest that there might be currently there is some works about transfer learning that can be trained on a set of source data set and then transfer the knowledge from the training data on source data set to the target data set with just a small amount of target log data set, and this can be applied for the new system. And yeah, that is from me to address the problem you suggest. Thanks.
Thank you, Van Huang. There is a question also from Liliana. Liliana, you can ask the question yourself. First of all, hello, ciao. And Liliana, hi.
Can you hear me? Can you hear me? Hello?
Yes.
Okay, so my question is related to the assumption of your logs. So how should your logs be implemented in order to discover an anomaly? Because we know that developers face a lot of difficulties in identifying the locations for logs, and information to be logged. So I'm wondering if you also consider how this log, where the log should be placed, and what information should the log collect in order to do anomaly detection successfully.
Yeah, actually, for where we should log, I don't think that I will have to answer for that question because it's related to source code analysis. So maybe there will be some somewhere in the code that you put the exception. You try to count the exception, and it's where you can place to write the log. And for the contents of log, it should have the bigger description for the current status. And maybe there will be some runtime information such as there are some code stopping code or error code that can be included in the log message that can help to automatically analyze log data. And yeah, for sure, for log, we will have the text formats for log, and we should record as many as possible data for log message. So yeah, so the annotation model can be applied for that. Thanks.
I just have a follow-up. Sorry. In your paper, I think you considered a semi-supervised approach, and I was wondering how well this approach can perform if the software evolves. So you have software updates, and maybe what was an anomaly actually is not an anomaly, it's just an evolution of your log because of a software updates. And do you think a semi-supervised model could deal with these cases?
Yes. Yes, thanks for the question. Actually, we also noticed that problem when during we do this paper. So for the semi-supervised model, there will be two types of semi-supervised model. The first type is that the model try to predict the next log event. So that is the type that cannot handle the case that you measured because it will treat any new log event as an anomaly. And then there is another type is that it is the PLE log paper, and it can understand, it can learn the semantic meaning of log, and then it form the it's use the unlabeled log data and normal log data to build a classifier, and then with that method it can handle the case that a new log event is appear. So yeah, so for some methods that can use the semantic vector, can learn the semantic meaning logs, and it can be used for the case.
Okay, thank you.
Thank you. So other questions? Other questions for our other presenters? We got 5 other presenters.
Yeah,
So
I have two.
Yeah. Okay. Thanks.
Okay. I have questions for Runhan. Okay. I have actually I have 2 questions. The first one is, first of all, I like the paper's topic and the approach you use. I think that the idea is very clear and most importantly, very intuitive. And my first question is, what's the performance if we only use password model or context model? Because that you only use something like voting mechanism to combine 2 models. So what's the performance if you only use one part or one model compared with the entire model?
As for this problem, since our we have 2 models, the password and the context model. Different models have the 2 models have different purpose. The password model predicts whether a candidate string is more password or not. This and the context model predicts whether the code snippet is used for prediction or not. So the two models have both good performance on their dataset, and we ensemble them together to finally have a prediction whether in the end-to-end ground truth we have a good performance. As for if we only use the password model, there could be much false positive, and if we only use the context model, actually we cannot directly use the result whether the context is used for authentication or not to determine whether it is a password or not. So we combine the result of both these 2 models.
Okay. Thank you for your answer. And my second question is an open one. So the context model you use are using code snapes, some surrounding code around the password string. And do you think some extra information, something like the function name or code comment, can help the context model or the entire model?
Pardon, could you please?
Yeah. I noticed that your paper, in your paper, the context model use code NAPIST. Yes.
Yeah,
and
code snippets.
Yeah. I think if you can use some extra information, something like the function name or the code comment, can help the context model.
Yeah. Actually our code snip is we have a range about the 6 line around our candidate strings. Actually the the comment is considered in our context. Yeah, we think it's a part of the code snip. However, as for the function name, actually it's for each candidate string, the function name is not easy to get, since it at least we should have a static analyzer to actually get the function name of the variable. So it's a little bit heavyweight for our task. So we just directly use the lines before and after the candidate strings, but not use the actually function detailed function name such in.
So the code snips are some sections, and not the whole function.
Yeah.
Oh, okay, I know. Thank you.
So thank you very much for the questions and the answer. Any other question?
Also a question for Renhan. Is there any way to evaluate whether the leaked password is harmful or it's just a leaked password?
Actually, it's a good question. Actually, we had tried some manual review since in our last part of the paper. Since we are not allowed to directly authenticate with this found password for ethic problem consideration. So we conducted a manual review to check whether the found passwords are sensitive or not. Maybe some are just used for test or demo purpose. I can't remember the exact data, but the sensitivity was about 80% in the whole found data set. Yeah, in our manual review.
Okay, that makes sense.
Thank you. Other questions for the other presenters? So while you think about your questions, I will ask a question. So I need to ask a question to Zhangji on the paper towards automatically repairing compatibility issues in published Android apps. I thought that this was a very interesting study, like the study of you all. And I was wondering, how do you expect to handle the installation of this tool? Like, I mean, do you expect that people will install this tool on their mobile, or these issues should be handled by tool developers? And please, like, elaborate a bit on how can this be released and used, and who are the users of this tool?
I think maybe the manager of the market or the developers, because we can repair the compatibility issues based on the published apps and then decompile it to source code, and that will benefit the development of the.
Okay, so managers, like not the users.
Yeah, not the users. I think users they still won't care about these things. They just know this app, I can use it or I can't.
Okay. Thank you very much. And other questions, guys? So I will ask a question to Li Zhen. Is Li Zhen is here? Yeah.
I'm here.
I wanted to ask you one question about the authorship attribution, topic, because authorship attribution methods can also be used in a malicious way, like, for example, to violate the privacy of authors. To what extent do you think this is an issue for your research? Like a malicious usage of authorship attribution, understanding who is the author of a certain code is also like can be some form of violation of privacy of the author.
The privacy of the author, you mean?
Yeah, because if I understand, if the code is written by someone, for example, in a company in which people are working together and the output of the work is just the code coming from the team, and you can pinpoint the actual author and say, hey, this author is not putting enough effort or is not contributing enough, while probably they are contributing in another way. So is this an issue or not? I mean,
This means an attack or code authorship attribution can point out the author, but it has some other situations we can use for code transformation, code plagiarism, or bug fixing, or such as this. I think this situation can use code authorship attribution. And I agree with you. Some privacies may leaked. Yeah.
Okay, thank you. And other questions?
Yeah, I also have a question for Zhenli.
Oh yeah.
And I noticed that the one input is a set of adversarial examples, and I wonder what it used in your model. I expected the input containing the trained programs and the target authors is already enough. So why there is a set of adversarial examples as your input?
You mean the input of a job-gen framework?
Yeah. Have 3 inputs.
Yeah, we have 3 inputs.
I don't know what is used for the input set of adversarial examples. So can you explain?
We want to defend the attacks about the adversarial examples. Some attacks use adversarial examples to use adversarial examples for targeted attack or untargeted attack. If we involve the adversarial examples and train the model, use this data to train the model, we can defend these attacks.
So it is like negative samples when train the model?
Negative examples.
Samples. Yeah.
Put the adversarial examples into the original training site and train the model. So the model can defend these types of adversarial examples, these attacks, yeah.
Oh, okay. Okay, thank you.
You're welcome.
Thank you. Questions? So I have a question for all of you, actually, because I think you've done a lot of interesting study, and many of you have applied deep learning or machine learning techniques. And I saw that you are using like extensive data sets. So my question is, how much effort did you take to annotate this data? And I mean, it's something, was it a problem? And did you have sufficient tool support to perform the annotation? So if you want to discuss this aspect for your specific case, someone of you could start, like, for example, Ting, did you use a data set and was it a problem?
My data set, I didn't use deep learning in my work, but I have a data set. This data set is built automatically via bug injection. So it can be gene automatically. So it's not a very big labor work.
For your case, so it was generated automatically, and so you didn't needed so much manual work. While, for example, for Zhangji, did you need manual work, or someone else did some very intense manual work for annotating the dataset? No, please answer. Like, for example, for the code authorship attribution, did you reuse an existing dataset, or you needed to annotate? Li Zhen, did you use a previously existing dataset?
Yeah, I use a large data set. The original data set maybe small, but the data set used for the Robgen framework is large, because they extend many other examples, input many other examples to the original data set, such as adversarial examples mentioned above, and some code perturbations, some examples generated by code perturbations. And I think the training time will be much longer than the model with the original data set, but it can obtain the robustness. I think it's benefits.
Okay, thanks. And I see, for example, Van Huang, did you need to annotate your dataset, or someone else did it?
Yeah, actually, I use public dataset, and there's someone that already label it. But
okay, so
the main problem.
Yeah.
Yes, actually, the main problem is that with that dataset, we only have the class of 1 or 0. So if we want to analyze and diagnose the fault, we cannot perform on those datasets. Yeah, we will need to collect our dataset for our study. Yes.
Okay, thanks. And Yaowang Wang, did you reuse a dataset, or did you develop it?
Actually, I annotated by myself and by our team, and I think it is a really challenging task and so time-consuming. And actually, I think we have some tools for annotation. Or actually, I think there is a good way is to firstly you can use some tools to generate some results, and then conduct a manual review, and that will be efficient. And actually, I to be honest, I don't like deep learning, and I think I will. And my future work don't use it, and we'll use some simple heuristic methods, or some unsupervised methods. I think annotation is really a big challenge task.
Yeah, and we need it in any case, both if we use deep learning and also if we use a rule-based system, because we need to show that our system actually works. So we need a gold standard somehow. And no, I'm asking this because I think it's one of the challenging issue, because for existing problems, there are some data sets, they are sufficiently large, but for new problems, like the effort that the researchers put in defining the data set is huge. And in the papers, it often emerges only the techniques and not the effort in generating the data set. That is a great contribution, because all other papers can build on that. So I think, do you have any other remarks about this aspect? Or do you want to say something final before we close the session?
Thank you.